Okay, welcome everybody to this sectional talk. It's my pleasure to introduce Pablo Shmerkin from University of British Columbia in Canada and Itala University in Argentina. And he will talk about slices and distances, two problems of Furstenberg and Falconer. So please.
Okay, thank you, Giovanni, for the introduction. It's a great honor to speak at the ICM and also here in Jerusalem. Thank you for taking care of the technical part. Hopefully it's fine. Yeah, great, wonderful. Okay, so I will talk about two problems which are very concrete and they look kind of innocent, but they are not. And they are both problems in fractal geometry, but other than that, they look quite different. So if I have time at the end, I will explain in what sense they are not so different. Okay, so the first problem, I'm afraid you cannot see the titles of the slides, but I guess it doesn't matter too much. Okay, so the first problem is a problem, I would say, at the sort of a boundary of ergodic theory, fractal geometry, and maybe a bit of number theory. So it's related to multiplication by p on the circle. So if you take a course in dynamics or ergodic theory, in the first few minutes of the course, you see some examples. And this is one of the examples that you see. So T is the circle, written additively, so 0, 1 with 0, 1 identified. And there I consider the map that is multiplication by P. So it just multiplies by P on the circle. And this map also has sort of a symbolic interpretation. If you look at the PRE expansion of a point in the circle, then a multiplication by PTP just shifts the expansion to the left. So from this symbolic point of view, it's pretty simple, although the shift map is very complicated in some sense. And then one can look at sets which are invariant under these maps. And okay, for many reasons, it makes sense to look at closed invariant sets rather than general invariant sets. And it turns out that there is a huge variety of sets which are invariant under a given map TP. So P is an integer at least 2 here. And for any such P, there are many, not in the sense of cardinality, but in the sense that there is no way of classifying them or understanding them all. In this sense, there are too many closed sets invariant under any fixed TP. And the simplest class of the simplest class of non-trivial invariant sets are generalizations of the Middle-Thirds counter set. So are sets where you forbid some PRE digits in the PRE expansion. So D here is the set of allowed digits. And then the set that depends on the base P and the allowed set of digits D, well, it's a set of all points in 0, 1 whose PRE expansion has only digits from D. So if P is 3 and D is 0 and 2, this is the Middle-Thirds counter set. And otherwise, it's a very natural generalization. And because this set is defined in terms of PRE expansions, if you shift the PRE expansion, you fall back into the set. So it's certainly invariant, and it's easy to see that it is closed. So for a given P, there are lots of sets invariant, closed and invariant sets under TP. But on the other hand, if you look at P and Q, which are different in an essential way, so they are not the same in disguise, and being different in an essential way means that they are not both powers of the same integer, because expansions to base 4 and to base 8, for example, are really expansions to base 2 in disguise, looking at, well, not in disguise, I would say, in plain sight. So looking at expansions 2 bits at a time and then 3 bits at a time. But the expansions in base 2 and 3, they are not the same in disguise. And this is because 2 and 3 are not powers of a common integer, or equivalently, log 2 over log 3 is irrational. So I'm always going to assume this condition of not really being the same base whenever I talk about two different bases, P and Q, and you can think of 2 and 3, just 2 and 3. Okay, so in this case, there are no non-trivial sets which are invariant under both these transformations at the same time. This is a beautiful and famous theorem of Hiller-Furstenberg from the early 60s. Well, of course, there are some sets which are invariant under times T and times Q. One is the full circle. The full circle, by definition, is invariant under everything. And also, if you look at, for example, P2, Q3, and the set is fractions with denominator 5, this is also invariant under times 2 and times 3. But other than finite sets of rationals on the full circle, there are no other sets which are jointly invariant under TP and TQ if P and Q are not the same in disguise. So this theorem is an early manifestation of sort of heuristics that we believe What we believe is that expansions in multiplicatively independent bases should share no common structure. Okay, so this is pretty vague. So one can make it slightly less vague by talking about invariant sets. So we have P and Q multiplicatively independent. Then we have two sets, A and B, which are closed and invariant under TP and TQ respectively. Then the still vague, but slightly less vague of the principle says that these sets, A and B, have no common structure. Now, these sets typically are uncountable sets of zero measure in the circle, and they're sort of fractal. So being invariant under times P or times Q is some sort of self-similarity. So you should imagine that they are fractal sets. So if we want to make this more precise, we should define what it means for these fractal sets to have or not have common structure. Okay, so maybe a very first definition that you can make is say that a set and itself has common structure, but otherwise there is no common structure. So this is like the coarsest or sort of the most basic possible definition of common structure. It's just being the same set. The set and itself have common structure, otherwise they don't. And if you adopt this definition, which again is not very refined, but we have to start somewhere, then Furstenberg's theorem says that in this sense, TP invariant and TQ invariant sets have no common structure if we adopt the convention that finite sets of rationals and the whole circle have no structure whatsoever. They are too simple, they have no structure. Okay, but one would like to be a little bit more refined and allow different sets to still have common structure. So how can we do it? Well, there is a very natural way. There is more than one way, but there is a very natural way, which is look at the size of the intersection. So we have two subsets of the real line. If the intersection is unexpectedly large, then we can think of A and B as having common structure. And the inspiration for this maybe comes from linear algebra, where you know what is the dimension of the intersection of linear subspaces in general position. If the intersection is larger than that, they are not in general position, so they have some unusual or extra common structure. Then how do we measure the sets? Well, there are several ways, but natural ways to measure them by house of dimension. So this is the size we are going to use for measuring these fractal sets. So what one expects for generically or typically in some sense, and there are many ways to make this precise, but I'm not going to go into that. What one expects is basically the same formula that one has for linear subspaces, which in this case means that the dimension of the intersection should be the maximum of the sum of the dimensions minus 1, or if this is negative, then 0, because the dimension cannot be negative. Okay, and then this motivates the conjecture of Furstenberg from 1969 that says that if A and B are invariant under times P and times Q, okay, we cannot have this equality, or maybe we can, but okay, so the conjecture is just an upper bound, saying that the intersection is not unexpectedly large. Maybe it could be unexpectedly small, but not unexpectedly large. And there is a strong version of the conjecture in the same paper that allows a perturbation of one of the sets by an affine map. So here, A and B are subsets of the circle, but the circle is written additively, so we can embed it into R, and then F is just a linear map in R, non-constant linear map in R. And the conjecture, strong conjecture, or strong version of the conjecture says that the intersection, again, of a times 2 invariant set and a linear image of a times 3 invariant set, including the identity, which is the most interesting linear transformation, satisfies this upper bound. Okay, so just to show you a picture, on the x-axis we have the middle-thirds counter set, on the y-axis we have times 4 invariant set. In fact, it's a forbidden digit set, so digits 0 and 3 are allowed, 1 and 2 are not allowed. This is the Cartesian product. And then looking at the intersection of these two sets up to an affine change of coordinates that doesn't change dimension is the same as looking at the slice of the product set with the diagonal, y equals x. And more generally, if we apply a linear perturbation to B, this is equivalent to intersecting the Cartesian product with another line. So essentially, we want to understand intersections of this product. Well, not essentially, it's equivalent to understand intersection of this Cartesian product with transversal lines. So we want to avoid horizontal and vertical lines, which are special because this is a Cartesian product. And in some sense, we have to count how many little rectangles these lines intersect. This is somehow the game we have to play. So here is the conjecture again. It says that times 2 and times 3 invariant sets, closed invariant sets, do not have too large intersection, even after linear perturbation. And well, now we know that the conjecture is true, and it was proved independently and simultaneously by Mengu of the University of Oulu and myself. 2016 is when we posted the preprint. In 2019, it was published. So unfortunately, I don't have time to say almost anything about the proofs other than some keywords. So I will say some keywords. So actually, in the paper where he stated the conjecture, Furstenberg introduced a method to attack the conjecture and made some partial progress. So this method is now known as CP chains. They were not called CP chains in the original paper. Now we call it CP chains. So this basically allows you to define dynamics on the slices. So you want to show that there are no large slices. So in dynamics, it's natural to put a dynamical system on the large slices. And Furstenberg showed that there are many large slices, but not enough to conclude the conjecture. And then Mengmu found a way to sort of refine the method to show that there are even many more large slices, and this was enough to deduce the conjecture. And he obtained these many more large slices as a sort of very unexpected application of Sinai's factor theorem, which is a classical theorem in ergodic theory. So my proof is completely different. It uses a little bit of dynamics, but not too much. So it uses some properties of uniquely ergodic cocycles, which is some dynamics, but not too much. But otherwise, it is strongly based on additive combinatorics, in particular, the Valox-Emery-Gowers theorem and some ideas of Jean Bourgain that I will talk about a little bit if I have time at the end of the talk. And it uses something called multifractal analysis, which in this case, there are some LQ norms of some measures. And the question is, what happens when Q varies? So this is what multifractal refers to. So these are fractal measures as Q varies, the LQ dimension behaves in certain ways. And this is sort of an object of studying multifractal analysis. And I was very much inspired by Mike Hochman's work on similar measures, which was the topic of Mike's presentation in the last ICM. Okay, and then there were some further developments. Han Yu sort of simplified Mengmu's approach completely bypassing CP chains. So he has a more elementary proof in some cases, not in all cases. And in some cases, he also obtained some more quantitative information. And then even more recently, Tim Austin found yet another proof, which has some features in proof with Mengmu's, but it's also very different. And it is by far the simplest. So if you want to read something beautiful today, before going to sleep, you can look at Tim Austin's proof. Okay, but he also uses Furstenberg CP chains from 1969. Okay, so this Slice conjecture turns out to have connections to several other things. So I want to mention some of them, and these are all very classical. It also has connections to some more recent developments or some more modern developments, including the smoothness of the similar measures, which is something I'm not going to mention today, but you can look at Peter Various' talk and proceedings article for this. Okay, so I mentioned Furstenberg theorem that there is no set which is closed and invariant under times 2 and times 3 other than the trivial ones. And this is a rather easy corollary of the slicing conjecture, which is actually pointed out in Furstenberg's paper already, because if the dimension, okay, so it's easy to see using the multiplicative independence that the difference set of A with itself has to be the full torus, using that it's closed and TP and TQ invariant. And then this implies that the dimension of A cannot be 0. And once it cannot be 0, you apply the Slice theorem to A and itself, because it is TP and TQ invariant. And then this tells you that the dimension has to be 1. But it is well known that the only invariant set of dimension 1 is everything. So that's the deduction. Okay, there was another conjecture of Furstenberg, which is not about slices, but about some sets, which is somewhat related. So the conjecture say that, again, if we have a closed and invariant subset under closed and invariant set under times P and times Q, then the subset has dimension which is as large as possible, has maximally large dimension represented by this formula. And it can be shown, it's not completely trivial. So it's a rather direct consequence of all the proofs that we have, but it's also an abstract consequence of the statement that the Slice conjecture implies the subset conjecture, which by the way was proved well, over 10 years ago by Mike Hochman and myself. But now we have more proofs because it's a consequence of the slicing conjecture. And the heuristics for this is that here we are applying the sum map, x plus y, to the Cartesian product. And heuristically, when is an image of a map on a product large, when well, in general, when is an image of a function large, when the slices, where most slices are small. But the slices of this sum map are are intersections of A and translates of B. And now we know that all slices are small. Not just most slices are small, but all slices are small. So this is why I think it's correct to think that the slicing conjecture is much stronger or more uniform than the subset conjecture. Sunset conjecture somehow says that most slices are small, but now we know that all slices are small. Small in the sense of not being larger than expected. Of course, well, for those of you who know, if you just talk of the Furstenberg conjecture or the times 2 times 3 conjecture, it refers to this conjecture, which is the measured version of Furstenberg's theorem that I mentioned in the first slide. It says that the only measures which are invariant under times 2 and times 3, Borel probability measures invariant under times 2 and times 3, are sort of the obvious ones, which are Lebesgue measure, Hart measure on the circle, measures supported on finite orbits, and convex combinations of them. And this is open, but it is a classical theorem of Rudolph, Johnson, and then there is a paper, Rudolph and Johnson, that this is true in some strong way if the measure has positive entropy or positive Hausdorff dimension. This is equivalent. And okay, so the intersection conjecture is stronger than the Sunset conjecture, and in fact, is stronger than a measured version of the Sunset conjecture, where you look at convolution of measures rather than sums of sets. And these resultant convolutions of measures that I proved with Mike Hoffman in 2012 easily implies Rudolph Johnson. So I'm not saying that this is the best way to, or the shortest way to prove Rudolph Johnson, not at all. There are much cleaner, more direct ways to do it. But in some sense, it shows that this is a key that opens many doors. And in some sense, I think it's not unfair to say that this Slice conjecture is maybe the strongest statement of Rudolph Johnson type that we have until now. So it's much, much stronger than Rudolph Johnson in the sense that it gives a very uniform version of the convolution of invariant measures problem, which immediately yields Rudolph Johnson. Okay, and finally, okay, so this is, sometimes I joke that this is the most difficult problem in mathematics. Well, I don't know, but it's certainly very hard. So it's another conjecture of Furstenberg from the same paper. He says that for any irrational number x, we can look at these two numbers. Okay, they are defined in maybe a strange way if you have never seen this before. So we look at the orbit of x under multiplication by p, take the closure, take the Hausdorff dimension. And what this measures is the complexity. In some sense, it measures the complexity of the base p expansion of the number x. And likewise, this measures the number, the complexity of the base q expansion of the number x. And these are numbers between 0 and 1. And typically, they are both 1. But this is not a conjecture about typical x, but about every x. So the conjecture says that these complexities sort of balance each other in such a way that if one is too small, then the other has to compensate and be large. So this is very, very hard, very, very hard. And well, but the Slice conjecture shows that the set of x for which this doesn't hold has 0 Hausdorff dimension. So it's basically trivial that the set of exceptions has 0 Lebesgue measure, but the Slice conjecture implies rather directly that the set of exceptions has 0 Hausdorff dimension. But I cannot tell you any x for which this holds. So it's this 0 Hausdorff dimension set is very implicit. So we know nothing about what it looks like. And unfortunately, the proofs don't really open a path to a proof of this conjecture. So not at all. Unfortunately, this is not the case, but okay, at least it is something. Okay, so now I'm going to switch to a completely different problem, or on the surface, completely different problem where there is no dynamics. So I apologize to the live audience in Jerusalem, but the problem is very easy to state. Again, it's very innocent looking, maybe even more innocent looking than the previous one, but believe me, it is not innocent at all. Okay, so the question is, how does the size of a set relate to the size of distances spanned by pairs of points in the set? So this is the question. So we have a set in Euclidean space, then we look at the set of Euclidean distances spanned by pairs of points in the set. So the question is, how are they related? Okay, so the most basic formulation of this problem involves looking at finite sets and counting sizes by cardinality. And in this form is a famous problem that was started by Paul Erdos, even though he didn't conjecture this in that paper. But I think he did conjecture it and offered some amount of money, maybe $500 for the resolution. Anyway, the conjecture is originating in the 40s that if a subset over D has n elements, then it spans roughly at least n to the 2 over d distances. By the way, here the problem is the lower bound. Upper bound is not interesting because a random set or a geometric progression spans n squared distances because all of the distances can easily be different. So this is not the game we want to play. The question is how small the set of distances has to be. Where is this coming from? It comes from a lattice. So if you have a lattice of n to the 1 over d times n to the 1 over d and so on elements, it spans, well, it has n elements and it spans roughly these many distances. So the conjecture is somehow that the lattice is the extremal configuration for this problem. And this is known to be true by a very important breakthrough of Larry Guth and Ned Katz in the plane, but it is open in all other dimensions. So it's only known in the plane. And again, this was a massive breakthrough. Okay, so what I want to talk about now is about sort of a continuous version or a fractal version of this problem where we measure the size of sets using, again, Hausdorff dimension instead of cardinality. So again, the question is, how do the dimensions now, the sizes measured by dimension of subsets of Euclidean space and the distance is spanned by the sets, relate to each other? Okay, and this is the conjecture. The conjecture, okay, actually, there isn't a conjecture. There are several flavors of the conjecture because Kenneth Falconer wrote a paper where he didn't state the conjecture. He introduced the problem. But I will state two versions of the conjecture. Here is the first one. If you have a set in RD, which is Borel, this is not interesting or not very interesting for non-measurable sets. The things are known and they're not very interesting. So this is fun for Borel or compact sets. Okay, so we have a Borel set in Euclidean space of dimension at least d over 2. The conjecture is that it spans a set of distances of full dimension because a set of distances is a set of non-negative real numbers. So this number is at most 1. So the conjecture is that as soon as the dimension is d over 2, the distance is spanned by the set have maximal dimension. And again, this would be sharp as witnessed by lattices. Okay, you cannot just have one lattice here because these are compact sets, but you can do a counter construction based on lattices. And this is what Falconer did in 1985 to show that if true, this would be sharp. Okay, and there is a variant where you assume that the dimension of X is strictly larger than d over 2. And then what you expect is that the Lebesgue measure of the set of distances then is positive. Not just full dimension, but positive Lebesgue measure. This is not true, just assuming this. Falconer using lattices show that you can get Lebesgue measure 0 if the dimension is exactly d over 2. But once you are above d over 2, the expectation is that the distances have positive Lebesgue measure. By the way, this is in RD, d at least 2. This is not interesting in R. In R, everything is known and not very interesting. And this is not true. So R is different because this is about curvature. About curvature, and you don't have curvature in R. Okay, so as I say, this is sort of the natural analog of Erdős' conjecture for finite sets. And it is open in every dimension. So both versions of the conjecture are very much open in every dimension. And so a natural question is, at least in the plane, the discrete case has been solved. Why don't the same ideas work for this problem? Well, maybe I'm not able to explain why. You should ask maybe Larry Guth, but they don't. Or maybe they work for some very special classes of sets, but certainly not in general. Okay, so I want to explain why this innocent looking problem is not as innocent. So Kenneth Falconer proved in 1985 that if you have a set of dimension d over 2 in RD, then the set of distances is at least 1/2. The conjecture is that it is 1. He proved that it is at least 1/2. So I want to explain why this 1/2 threshold is hard to beat. And already beating 1/2, which is known, as I will explain, was an achievement. Well, first of all, if instead of Euclidean norm, you take the L infinity norm, for example, then 1/2 is sharp. So it is the curvature of the Euclidean norm that makes the conjecture plausible. In fact, this is believed to be true for any norm that has a smooth unit ball and positive curvature or non-zero curvature everywhere. But it's not true for polygonal norms. So curvature has to play a role. Okay, this obstruction is there, but maybe not so overwhelming because it happens all over the place in analysis that curvature plays a role and things fail completely for flat things. So this is very common and maybe is the smallest of the obstructions. Okay, the second one, I would claim that is quite a bit more serious. So suppose that you have a Borel subring of the real numbers, R of the Hausdorff dimension 1/2. R is this object, and you take the default Cartesian product with itself. R times R times R, D times. R, a Borel subring of the reals. You take a Cartesian product with itself D times, morally it has dimension D over 2, because the original set has dimension 1/2, you take the default Cartesian product. In fact, it has dimension at least D over 2, which is the right direction for what I'm saying. But what about the distances? So if you square the distances, well, you don't leave the ring. R is a ring. So the distances squared leaving the ring, and taking square root doesn't change dimension. So the dimension of the distance set is 1/2. So this looks like a counterexample to the conjecture and even to breaking the 1/2. But this is not a counterexample because this object doesn't exist. There are no Borel subrings of the real of dimension 1/2. But this was an open problem for decades. And so it's not easy, although there were two simultaneous proofs, and one proof by Edgar and Miller is quite elementary, ingenious, but elementary. So in retrospect, one can say this was not so difficult, but it was open for decades, and it represents an obstruction. For example, it says that over C, the analog of this is not true because the complex numbers do have a half-dimensional subring, which is the reals. So the order structure of R must play a very important role in any approach to the problem. And so sort of any progress on this problem, in particular breaking this 1/2 bound, either has to reprove this difficult theorem or long-standing problem, or it has to use some proof. And I would say that the last sort of obstacle maybe is the most serious one, or was considered the most serious one. So now we sort of know how to bypass it. But it was considered a serious, really serious obstruction for a while. And let me show you a picture. So the problem here is that in order to make progress on this kind of problems, you have to discretize them as some scale delta and try to prove a delta discretized version. So you want to show that it is true at a fixed scale delta. We don't know of any other way to do it. But if you take the most naive discretization of the problem at scale delta, 1/2 is again sharp. So this is the problem. So you cannot be naive. So there is a natural notion of Hausdorff dimension for sets defined down to resolution delta that was essentially introduced by Katz and Tao. This is not the version of Katz and Tao, but it says that so a set is a delta set, which basically again means S-dimensional at scale delta, if it doesn't intersect an R ball it intersects an R ball in, this is just measure because these sets are not fractal, they are union of delta balls. So it satisfies the Frostman condition from scales delta to 1. So this is, if you haven't seen it before, it may look strange, but this is a very common and also natural way of discretizing fractals. And this set here is a very beautiful delta 1 set. So it is like a one-dimensional, it behaves like a one-dimensional set at scale delta. So these rectangles have size delta times square root of delta, and the spacing between the rectangles is square root of delta. And it is a delta 1 set, very easy to see. But the set of distances, it looks like half-dimensional rather than one-dimensional, half-dimensional. So it has very few distances because of the curvature. So the distances from points here to points here. So basically from here to here, from a point here to points here, all the distances are the same at scale delta. So there are very few distances. So there is no distance set conjecture discretized in this way, which is the most natural way of doing it. Okay, so because of these reasons, I hope I convinced you that it's not so easy to go beyond 1/2. And well, it is true that one can go beyond 1/2 in the plane at least. And this follows by combining a paper of Katz and Tao and a couple of years later by Bourgain. So Katz and Tao proved that certain statements in discretized fractal geometry are equivalent. And then Bourgain proved one of them. And then by combining both things, one gets this. But the epsilon, first of all, it was not made explicit, even though all the methods are effective. So one could make it explicit, but it would be a lot of boring work and it would be very, very tiny. So imagine 10 to the minus 100, just to give you, I don't know what it is, but imagine 10 to the minus 100. So really, really tiny. Okay, so now some theorems, some of the things I've been working on more recently. Well, first of all, with Tamashkeleti, we obtained explicit bounds, but unfortunately we had to cheat. And in the plane, this is in the plane, we assume that the Hausdorff dimension is strictly bigger than 1. Not 1, but strictly bigger than 1. And this is, I would say, a quite substantial cheating, because once the dimension is strictly larger than 1, the second and third obstructions just go away. So it's much easier to see that there is no Borel subrings of dimension 0.50001 than 0.5, much easier. And you cannot have this discretized counterexample if the dimension is bigger than 1. But even then, even though we cheated, even with cheating, nothing was known. So it was not known how to exploit this cheating, and we sort of find a way to do it. And we proved explicit bounds. So the numbers are not so important, but we show that the distance has dimension at least 0.7, in fact, a bit bigger. In fact, this bound comes from a later paper, but it's very much based. So the work was really done here with Tamashkeleti. Sorry. Then if you know what packing dimension or upper box dimension or upper Minkowski dimension is, for that, we prove the much larger bound. So this is already close to 1, although it's not 1. This is double cheating because Minkowski dimension is larger than Hausdorff dimension. So we cheat twice. By cheating twice, we're close to 1. And then much more recently, together with Hong Wang, we were able to get results also in the critical case when the dimension is equal to 1 in the plane. And again, we got some lower bound, which is actually the golden ratio, but this is just a coincidence in some sense. So it comes out of some technical calculations. It doesn't have any particular meaning. But the point is, it is a number which is, I would say, macroscopically larger than 1/2. So it's not some, so this is not, so I want to emphasize that this is not looking at, Katz, Tao, Bourgain, and going through the calculations and doing them a little bit more efficiently. This would never, ever give you this number. So it's something different, although it uses many ideas of Bourgain in the background. Okay, and also we got something in R3, some bound in R3, which is new. You see nothing in R3 before. And in fact, we got bounds also in RD, but for the lower Minkowski dimension of the distance set. So a little bit of cheating, not for Hausdorff dimension so far. Okay, so there has been another sort of very long and fruitful line of research concerning more the second version of the conjecture, where you want to, okay, so we have a problem that we cannot solve that is an if-then. So if the dimension is this, then the dimension of the distance set is this. So we cannot solve it. So there are several things one can try to do. One is just assume the original hypothesis of the problem and try to see what we can deduce. And this is what we did in the previous slide. Another thing you can do is assume more in the hypothesis to reach the conclusion that you want. And the conclusion that you want is positive measure for the distance set. And the question is, what is the least we can assume? And what we would like to assume is that the dimension of the set is bigger than d/2, but this is open. But it was proved this d/2 is replaced by a number which is a bit larger, and there is a distinguished line of very deep research in this direction. So to prove this, one has to use very deep harmonic analysis, ideas related to restriction, and more recently to decoupling. And in blue are people who contributed to the problem in the past, and in purple you have the current world record holders. So there is a combination of papers that give these current best bounds, which are d/2 plus 1/4 in even dimensions and a bit more in odd dimensions. Okay, and if you have a problem that I cannot solve, there is a third thing that you can do that maybe is the most natural in some sense, which is look at some special case, interesting special cases. And this is the content of the next slide. So, so what is a natural class of sets of dimension S to look at? I would say that Alford's regular sets is a very natural class, so it's studied all over the place in analysis. So just to remind you, I said if S Alford's regular, if the S dimension Hausdorff measure of balls centered at the set have mass comparable with R to the S up to, well, not universal, but up to constants that are uniform in the center of the ball and the radius of the ball. So C can depend on the set X. In this sense, it's not universal, but it's uniform for the given set. Okay, so for example, the Sierpinski triangle or gasket or the Milthorf-Cantor set, these are Alford's regular sets, but this allows a lot more flexibility. So the sets don't have to be self-similar or have any dynamical structure. And for these sets, recently with Hong Wang, actually the prepping was posted in 2021. The paper hasn't been accepted yet. We showed that the conjecture, the dimension version of the conjecture is true for Alford's regular sets in every dimension. So it was not known even in the plane. We proved it in every dimension. And in fact, we proved something much more general. We proved it under the assumption that the set has equal Hausdorff and packing dimension or equal Hausdorff and upper Minkowski dimension if you prefer. And this is actually a much larger class than Alford's regular sets. And just a quick comment, since by some miracle I seem to have time. Noam Solomon, Larry Guth, so this is the wrong order of authors, so let me try again. Larry Guth, Noam Solomon, and Hong Wang have proved as a corollary of some incidence theorems for tubes in R3 that the dimension holds for a class of sets that are maximally separated, which is in some sense only in the plane, but in the plane they show that the conjecture holds for sets which are maximally separated, which is like the opposite end from Alford's regular. Is like, yeah, the opposite end. So I think this, unfortunately, the methods are very different and we don't know how to interpolate. But I think this still gives very strong evidence for the validity of the conjecture. Okay, so the Falconer distance set problem, I think it was introduced because it was a very natural, nice problem in itself, and a very natural generalization of the Erdős distinct distances problem. But as it often happens, people try to solve it, and trying to solving it found connections to everything else in some sense. So let me mention some of these connections, and all of them really, so they have Hausdorff dimension formulations, but really the interesting part is looking at the delta discretized versions. So in all of the things that I'm going to mention in this slide, we have sets which are union of delta balls, and they look S-dimensional or T-dimensional in the sense that I defined a couple of slides ago. If you don't remember it, it doesn't matter. So imagine sets of dimension S or T defined down to some resolution delta. Okay, so a very important problem is in this setting, well, this is a more general problem. So if you have a subset, even in the integers, X, one believes and hopes that either the sum set or the product set is very large. In fact, even maximally large in some sense, but this is open in pretty much every setting, in particular among the integers. And then one can also ask this question in this sort of discretized setting, where the sets are delta S sets, or, well, there is just one set here. So the conjecture is that if one has a delta S set, where S is not 0 or 1, then either the sum set of the product set is much larger than the original set. So another line is looking at orthogonal projections. So this is a very classical topic in fractal geometry, looking at orthogonal projections. And then one can also look at this in this discretized setting. And I want to emphasize here that we have a set that we are projecting in our D, and let's say we project to R. We can also project to, we can look at higher round projections, but let's say we project to R. We have some set in the circle or in projective space that gives us the direction, but I'm not looking at all directions. This is quite well understood. I'm not looking at all or almost all directions. I'm looking at possibly a quite sparse set of directions. And the question is, what can we say about the size of typical projections of this set by directions in this set? Then there is radial projections, which are a generalization of linear projections. So if you look at radial projections from the line at infinity, these are linear projections. So this is more general. So here we have two subsets of the semi-Euclidean space. And then we look at basically the direction, so the projective direction generated by X and Y. But you imagine that one point is fixed, and then you see this as a function of the other point. So this is called the radial projection. And finally, there is a problem of incidences. So of course, in combinatorics, there is a big focus on incidences between points on lines. Well, this is very classical, and then you can try to generalize in many ways. And again, we can try to bring this to the discretized world. And as a general rule, in the discretized world, everything is more difficult, with no disrespect to people working in combinatorics. So in combinatorics, a lot more is known, a lot more. And we sort of try to fall behind, we go behind them, trying to get some inspiration from them, and trying to do something, but it's kind of hard. Okay, so I'm not going to mention any results in any of these directions, but I do want to mention that the progress that I mentioned in the Falconer distance set problem goes in parallel with progress in all of these problems. So they sort of reinforce each other. So I have some work in each of these problems with co-authors, and there are also works from other people that then I used for the Falconer distance set problem, and ideas that we introduced in order to study the Falconer distance set problem, feedback into these problems, and so on. And this is very much ongoing right now with different people. So there is quite a bit of progress. But at the same time, there are no definitive results in any of these problems. So they are all very hard, and there is a lot that we don't know. Okay, so these two problems that I talked about, the Furstenberg slice problem and the Falconer distance set problem, okay, they are both problems in fractal geometry involving Hausdorff dimension, but other than that, they don't seem to have too much in common because Furstenberg's conjecture deals with sets with a very strong dynamical or arithmetic structure. So sets invariant under times 2 or times 3. And also it's about linear slices. So it's a linear problem in some strong sense. While the Falconer distance problem is about general sets. There is no dynamics whatsoever. It's about general sets. And also, as I mentioned before, it's very much about curvature. So yeah, it's related to curvature in some essential way. So it's a very nonlinear problem. Okay, but still, in my work on these problems, and works well, by other people, but also by myself, there are sort of common themes. So one of them is that I like projections. So you give me a problem, I try to translate it into something involving projections. And if I can't, then unfortunately you will have to ask somebody else. But if I can, then I can try to do something. And in particular, my solution of a Furstenberg slicing conjecture is really a result about projections, but dimension of projections, but a very uniform notion of dimension that as a immediate corollary gives well, the conjecture. So it tells something about slices as well. But it was important for me to look at it as a problem about projections. Then I was very much inspired by Bourgain's discretized sum product theorem, which is basically so Bourgain's discretized sum product theorem provides non-trivial lower bounds for this problem. And this appears either directly as a black box, or the proof appears at least as inspiration, and well, sometimes more than inspiration, in my work on all of these problems. So it's very much all the time in the background. And then something else that is important in all approaches is sort of a multi-scale approach. Okay, a multi-scale approach is somehow what you expect or unavoidable because we're looking at fractal sets. But somehow a multi-scale approach where we want to study the dimension of the set, which is some global number. And we do that by looking at what happens locally. Somehow there is a local to global principle in both problems. And also there is some combinatorial input that I'm going to try to mention in the remaining 3 minutes. So I haven't had the warning that there are 5 minutes left, but I will assume that there aren't 5 minutes left. Okay, so this is a very simple lemma, a bit technical, but very simple, but that has had a huge influence in my research. So when I learned about this lemma, so I knew that my life would change somehow. It's very, very simple. So it just shows that I'm very slow. I wasn't able to discover this myself, which is very simple. But still, it changed completely my outlook on how to attack this sort of problems. Okay, so what the lemma says is that if you have a probability measure defined up to some scale, then you can find a subset with large measure. So ignore this one completely. So a subset with almost one measure in some sense, so large measure, in such a way that if you look at intermediate scales, all of the dyadic cubes of positive mass have the same mass once you restrict the measure to this set of large measure X. So you restrict to a set of large measure and you get a very uniform measure in the only sense that you can expect to have this. And again, uniform measure means that at every intermediate scale, every dyadic cube has the same mass, roughly, up to some factor of 2, say, and this mass is a number rho j, where j is a scale. And then I have a measure, which is any measure, and then I get a sequence of numbers, rho j, and it's much easier to study a sequence of numbers than a measure. So what I do is somehow I study the sequence of numbers, or I study the measure via the sequence of numbers. And again, this is extremely simple, but it can lead to new things by some mysterious reason. So, right, so somehow this rho j, in the way I stated it, I guess is a decreasing sequence. So whether it decreases like this or more linearly indicates some sort of qualitative behavior of the measure. And okay, so for the Furstenberg conjecture, I had to show that because I'm dealing with, okay, the conjecture is about invariant sets, but I do it via measures, invariant measures. And I had to show that these invariant measures, because they are invariant, they are not general measures, but they are invariant, these branching numbers are sort of intermediate. They are not maximal or minimal. So I know something about these rho j's using the invariance of the measure. And this is like a very important part of the proof. And this sort of idea is definitely not new. It was used by Mike Hoffman and by Bourgain and by other people before. But what is new is the LQ norms that appear here. That unfortunately, I only have 1 minute, so I cannot tell you anything more about this. But in Falconer's problem, the sets and measures are completely general. So the rho j can be anything. But based on the rho j's, so there is this multi-scale decomposition. But something which is new, which again is extremely simple, but again, mysteriously leads to some interesting new things, is that one can use these rho j's to choose the scales in the multi-scale decomposition, depending on the measure. So you give me a measure, that measure gives me some rho j's, and I combine the rho j's in blocks to do what I want. And like 5 of my recent papers basically the idea is different ways of choosing the blocks of row J's in a way that is convenient for the problem. So again, very simple, but somehow useful. Okay, so at the end of the day, I have 20 seconds left. So let me tell you that both these problems and many other problems can be restated in trying to understand the distribution of fractal measures in tubes, which looks very innocent, but maybe it stops being innocent if you think that the Kakeya problem, for example, is of this form. And okay, so we know more than we knew a few years ago, but certainly we know very little still. So still almost everything needs to be done. And there are more details in my proceedings paper. It's still a broad survey, but there are more details there. And thank you very much for your attention.
Thank you, Pablo, for your very nice talk. And I think I have only time to say hello because they are cutting us off. Okay, thank you very much.
Thank you, Giovanni.
Bye. Goodbye, everybody.